Finally, let's show for the very specific case of our Maxwell theta operator that the eigenvalues are not only real, but they're also positive. And the way we're going to do that is by making use of some intermediate step that we had when we were trying to show that the theta operator was actually Hermitian. And there at some point we had the following. We had that f theta of g was equal to the volume integral of the curl of f complex conjugate, and then here we had the following terms integrated out over the volume dv. So this is something we had earlier. Now what we're going to do is we're going to replace both these guys with an eigensolution, with an eigenfunction of our theta operator, namely h. So pause the video, do that substitution, and try to interpret all of the different factors that you have and see if you can conclude from that that in this case the eigenvalue is also positive. Okay, so let's replace everything by h. So we have h theta h equal to, and then we have the volume integral. So of course, yeah, 1 over epsilon we have over here. And then these guys, they become basically their complex conjugate of each other. So this will end up being the norm squared of the curl. So this becomes curl h norm squared dv. Okay. And if we make use of the fact that h is an eigensolution, an eigenfunction of the theta operator, we can also write the left-hand side as being omega squared mu. And then we have h, and then just copy and paste the volume integral of 1 over epsilon curl of h norm squared dv. And then let's just interpret all of the different factors that we have. We know since a long time, since the properties of the scalar products, that this guy here is a positive number. Okay. Likewise, this is also a norm, so this would also be a positive number. And let's look at this guy over here. Now here we need to make a certain specification. Let's say that we're working with not only lossless materials, but also lossless dielectrics. And if you're dealing with lossless dielectrics, then you can also conclude that this guy here is a positive number. So all of the different factors over here, they're positive. So the right-hand side is a positive number. The left-hand side, therefore, should also be a positive number. But since this factor is a positive number, the only inescapable conclusion is finally that the eigenvalue omega squared mu is also a positive number. And since we're going to say that we're working with non-magnetic media, so we don't need to worry about the mu, and we can finally say that omega squared mu is, that omega squared is a positive number. And that, of course, means finally that omega itself, if we take the square root, that this is going to be a real number. And this is precisely what we were after. We wanted to show purely mathematically that our physical intuition here was correct. But I do want to stress the fact that the eigenvalues are not only real but also positive is not a general property of Hermitian operators. This is only true in this particular case for the very specific structure that we had for this operator over here. But don't generalize this to arbitrary Hermitian operators.